Got so all these operators here, both those and some of them we had before, we can write as, and that was in a way part of the exercise, we can write them as the external perturbation, and we had some before which then looked like some other operator times the magnetic field. And we had one with the electric field also, which I think I called F. So we had derived operators which looked like this, and we on purpose, or I on purpose, wrote them all in a way that I could write them like this. So I had clearly separated the external fields or the internal magnetic moments from terms which depended on electronic coordinates. So this is independent of the electronic coordinates, where all the electronic coordinates are in here. And so we got several of those. I mean, this would be, for example, spin dipolar, paramagnetic spin orbit. And we also had, and they are all first order, and then we also had some terms where we had sort of two perturbations, which then basically means that must be a tensor operator. For example, two magnetic fields. I think that one we called then pi xi. And we sort of had all the mixed ones also. And then here with two different magnetic moments. And all those were, the names for all those, they all start with diamagnetic. This was a diamagnetic shielding, that's the diamagnetic spin orbit, and this is just a diamagnetic contribution to the magnetizability. So, we'll collect them now all. We finally end up that our Hamiltonian, in the presence of external electric and magnetic fields and internal magnetic moments, is our original Hamiltonian, which you sort of could call the field-free electronic Hamiltonian. It's just electronic Hamiltonian, because we are in the Born-Oppenheimer approximation. And then you get a term with all first order term with all the terms which are linear in the fields or magnetic moments. And this second order term which are quadratic in fields or magnetic moments, or sort of mixed bilinear, as some people call it, if it's linear in the field but also linear in some other perturbation. And in a way, this might sort of look not strange. This term is a bit strange, that you get this second order term. I mean, you probably have not seen perturbation theory with having a second order term yet. But that comes about because the vector potential enters into the kinetic energy term. It's an extra contribution to the canonical momentum, and since the kinetic energy term is the canonical momentum squared, or it's actually the mechanical momentum squared, we get something with the vector potential squared. So if we write that out now, what we finally have then, we have this P1 operator, P1 xi operator with the external magnetic field. And to repeat a bit from Tuesday, this operator, if you sort of look at that, this must be the magnetic dipole moment of the electrons, and it can be either the angular magnetic dipole moment or, and this one xi is the angular magnetic dipole moment, and we also have a term with the spin dipole moment, this one. And the angular momentum dipole moment, that is essentially really the angular momentum operator. And then some factors which are like here, corresponding to those, are just the gyromagnetic ratio. The ratio which transforms, between the magnetic moment and the angular momentum. Then we got a term, it's said, which depends on nuclear magnetic moment, and that was called the PSO term, PSO contribution. And again, I just keep it with one nucleus, at least there. Then we got this term coming from the spin, so it's a spin dipolar, SD. Again, also times the nuclear magnetic moment with its limiting term, which is the Fermi contact term. So these together are the same interaction. It's the electronic spin and the nuclear spin, but it turns out to be sort of two terms. And then we finally had a term with the electric field. And like here, this PF is just the electric dipole moment of all the electrons, or it's minus the electric dipole moment of the electrons, which goes in there. And then the H2, let's continue there, so that should be H0 plus them, and then we get those three H2 terms, and let's write them up. P2, that's a tensor, and not a vector anymore, psi times B. What do I call the other one? DS. MA P DS, also a tensor, times the magnetic field. And that, because it has magnetic moment, gets an A also, plus the final one, which is P, that must then be AB, because it's 2, and that's the diamagnetic spin orbit term with 2 magnetic moments. Right, so that was basically I think task number 1, which we started on Tuesday, to get the fields, external fields and the moments into our Hamiltonian. And the way we do that is, as we discussed on Tuesday, is we use the semi-classical minimal coupling approach, where we treat the fields and the moments classically, and we treat them through, not directly through the fields, but through the potentials. And the scalar potential is just added to the Hamiltonian and then multiplied with the charges of all the particles. And the vector potential enters, as I just said before, enters into the kinetic energy term because it's part of the mechanical momentum. And then filling all in, we get all those terms now. So these are all the possible questions we want to look at